theorem, if V belongs to Rn is an eigenvector of matrix A associated with eigenvalues lambda, then V is also eigenvector of of e raised to a associated with e raised to lambda. So here given part is, say, given this is the given part. Up to this it is given, and this is what our claim. So given v belongs to Rn is an eigenvector of matrix A associated with eigenvalue lambda. So this is what given part, and our claim is, we want to prove here, claim V is also eigenvector of e raised to a associated with eigenvalue e raised to lambda. That is, if lambda is eigenvalue of matrix A, then e raised to lambda is eigenvalue of matrix e raised to A. This is what we want to prove here. So first of all, as we know that the Maclaurin series expansion of, writing here, Maclaurin's series expansion of e raised to x is, so what is Maclaurin series expansion of e raised to x? It is 1 plus x square by 2 factorial plus x cube by 3 factorial plus x4 by 4 factorial and so on. So we can write this as summation k equal to 0 to infinity x raised to k divided by k factorial. So this is what the Maclaurin series expansion of e raised to x. So e raised to x is equal to summation k equal to 0 to infinity x raised to k divided by k factorial. So we are going to use this expansion to prove this theorem. So now since given V is an eigenvector of matrix A, what is given here? V is an eigenvector of matrix A associated with eigenvalue lambda, then by definition of eigenvalues we can write a raised to av is equal to lambda v. This is by using definition of eigenvalue. So now, so consider here e raised to a v. So e raised to a v, by using the definition of, since e raised to x is what? E raised to x is equal to summation k equal to 0 to infinity x raised to k divided by k factorial. By using this formula we can write this as summation k equal to 0 to infinity e raised to x. So it is a raised to k divided by k factorial into v, into what? V. So but now a raised to kv, since we have already proved this theorem, a raised to kv is equal to lambda raised to kv in previous theorem. In previous video you can check this. If lambda is eigenvalue of a, then lambda raised to k is eigenvalue of a raised to k. So by using this we can write this as summation k equal to 0 to infinity, the value of a raised to k into v is lambda raised to k v divided by k factorial. But this is nothing but This is equal to summation k equal to 0 to infinity. Since this summation depends on only on k, so this is equal to lambda raised to k divided by k factorial into v, and the value of this term is equal to e raised to lambda into v. Okay, so e raised to av is equal to e raised to lambda into v. What this implies? This implies e raised to lambda is an eigenvalue of e raised to a associated with an eigenvector e raised to what is here associated with an eigenvector phi. So